Hey guys, Miss Michelson here. Today we're moving on to section 5.3 in Advanced Algebra 2. So if you want to go ahead and get your workbooks open, I am at the top of page 234. Look at example number 1. We want to graph a square root and a cube root function. So I went ahead and drew my axes on here to make things a little bit easier for myself. And we also are going to identify the domain and range for each of these functions. Now, we do know that we have a nice, beautiful, lovely graphing tool called Desmos for us, that if we wanted to get a nice picture of what this graph looked like, we could take both of our functions here and just type them into Desmos. But it's nice to know kind of the basics of each of these functions, the square root and the cube root functions, to hopefully make maybe the Math Excel assignments go a little bit faster. So the first thing we want to talk about is what this idea of our parent function. We've talked about those before in like section 1 and section 2. A parent function is just the most basic function of that type. So our parent function here is our like square root function. There isn't any transformations. We're not adding, subtracting, multiplying by any number. All we're doing is taking the square root of x. So that's actually where we're going to start on our graphs. I think this is the way my brain thinks about it, and I think it really helps you out if we start by looking at the parent function first. So I'm going to pick a color to write that one in, and it's going to be green. And the best way to get a picture of a graph by hand is by making a t-table. So, in a t-table, we're allowed to pick any x value that we want, and then we just have to calculate the y value. Now, we want it to be able to take the square root of that number, so we want to choose nice x values. Normally, I do like -2, -1, 0, 1, and 2, so we get like a close picture around the origin. But we know that we can't take the square root of 2, so things that might be a little bit nicer for us are our perfect squares. I'm going to do 0, and I can take the square root of 1, but my next perfect square wouldn't be 2, 3, 4, 5, it would be 9. So I'm going to put 0, 1, and 9 on my graph, and we'll see if it fits on this page. But let's talk about another thing. Do I need to include any negative numbers here when I'm making my parent function or my parent graph of just my square root function? We know that we're allowed to take the square root of negative numbers. However, their answers turn out to be imaginary, and we do not see imaginary points on our xy coordinate plane. So for all of our purposes of graphing these functions, the square root of -2 is imaginary. It's not going to show up on our graph. The square root of -1 is imaginary. It's not going to show up on our graph. If you want to make yourself a little bit of a note why it doesn't matter to us here, just make a little star and say it's an imaginary number. But once we get into our positive, these are where things start to work out nicely for us. The square root of 0 is 0. The square root of 1 is 1. I could have put 4 in there. Let's put 4. The square root of 4 is 2, and then the square root of 9 is 3. I forgot a perfect square. So this will hopefully give us a nice picture of what our parent function looks like. 0, 0 is at the origin. 1, 1, so I go over 1, up 1. And then 4, 2 means I go over 1, 2, 3, 4, up 1, 2. And then over 1, 2, 3, 4, 5, 6, 7, 8, 9, up 1, 2, 3. So we get this picture, if we kind of connect our points here, of a radical function. And there are some key features about this radical function that we should talk about. Notice that it's only in the first quadrant, which means all of my x values and all of my y values are always going to be positive. So based on our transformations, we can shift these around a little bit more. We can end up in any of these quadrants, but the most basic one is only all positive numbers here. But we want to take a look at our function here. I called it g of x, and I'm going to make a new t-table to see what this function here, the square root of x minus 5, is going to look like. And if we kind of take a peek at example number 2, or take some of our previous knowledge about what we know about transformations of functions, maybe we can get an idea of what this graph is going to look like. But again, we are allowed to pick any x values that we want, but we want to make smart choices here. So if I did -2 -2 minus 5 is -7. And if I take the square root of that, it's still not going to work. So let's start our table with 0. So what happens when I take the square root of 0 minus 5? That is just the square root of -5. That's not going to show up on our graph. So, and if I do 1, it's still going to be a negative number. If I do 2, it's still going to be a negative number. If I do 3, it's still going to be negative. What happens if I choose the x value 5? I'm taking the square root of 5 minus 5. 5 minus 5 is 0. The square root of 0 is 0. So that one is going to show up on our graph. That one's nice for us. If I do 6, what happens if I do the square root of 6 minus 5? That's the square root of 1, which is 1. So that one's going to show up on our graph. And we can pick some more points. Let's try another one. The idea is that we want to get a perfect square underneath of our radical, right? So our next one is 4. So what minus 5 equals 4? 9. So we do 9 minus 5 equals 4. The square root of 4 is 2. So that should give us a nice start to our graph to see what our function is going to look like here. So the first one real point that we're going to see is x is 5, y is 0. So I'm going to go over 1, 2, 3, 4, 5, put a point on my x-axis. And if I go over 6 up 1, and then over 9 up 2. So the idea is when we're kind of like graphing our functions or transforming our functions is, actually, I'll talk about that more in our second example. This is just our new function here, g of x. And maybe we can kind of see what that -5 did. How did it move our function? And then the last thing we want to do is identify the domain and range. So domain is going to be our x values. What's my lowest possible x value? What's my highest possible x value? I'm going to write these as an interval. So x is never getting smaller than this point. It's only getting larger. And it's a closed circle there. X is going to be greater than or equal to that value there is 5. And then our y values, our range, y is never a negative number. It's always going to be positive. So y here, because we never go below the x-axis, is always above it, y is going to be greater than or equal to 0. And the last thing we want to do is define if the function is increasing or decreasing or where it's switching. So this one, you can see it's only going up as we read our graph from left to right. My finger is tracing upwards. It is always increasing. So what we want to get from that example, we want a general idea of what the parent function looks like. So that's my green graph right here. And then we want to know how we can graph these by hand. Our g of x function, that's my red graph. But I'll show you kind of like my little hint or little trick in the next example, example number 2. But before we move on, we need to do part B. But this time, this is not a square root function. This is a cube root function. So the best place that I found to write this is over here, down in the blue section down here again. Our parent function first, let's try to calculate that graph for us. Now, a cube root, we are allowed to take the cube root of a negative number. So that is something just to make a mental note of, we're allowed to do it. So our perfect cubes, I always like to start with 0. And then 1 is a perfect cube and 8 is a perfect cube. And then we can include the negative forms as well. So we'll do -1 and -8. So if we want to calculate, the cube root of -8 is -2. The cube root of -1 is -1. The cube root of 0 is 0. I'm writing really small here to fit this in. The cube root of 1 is 1. And the cube root of 8 is 2. So we now have calculated our, like, I wouldn't want to say basic, but our starting points of our parent function. Again, on our graph, our parent function has the point 0, 0. So I have to go back up here and put this at the origin. My next point was over 1 up 1. And then we had over 8. 1, 2, 3, 4, 5. It would probably be somewhere around here. And then if we go into our negative side, it was -1 down 1. And then it was -8 down 2. So instead of like our square root function being contained in the first quadrant, this one is allowed to be negative and positive at the same time. So we get this weird kind of like S. It's kind of like an elongated S, which is our parent function. So now, again, just like we did in our last example, let's go ahead and calculate our new points of our function here, g of x. So we're taking the cube root of x plus 1. So we'll kind of figure out what that plus 1 does in our function. So again, best way to graph by hand is just by making a t-table. We want to pick smart choices for our x values here. So we want to be able to take the cube root of them when we're adding 1. So I always like to think of what's going to make underneath my radical 0. That's kind of where I want to start. So if I had -1, I take the cube root of -1 plus 1, which is just the cube root of 0, which is going to be 0. So I'm always looking for that like initial point, and then I want to go up from there. What's going to make the cube root 1? So what does my x value have to be to get 1 underneath my cube root? It has to be 1. So we'll take the cube root of 1 plus 1. Wait, that's 2. It has to be 0. Going crazy. 0 plus 1 is 1, and the cube root of 1 is 1. We also could take, like, if we did positive 1, let's take a look at that. The cube root of 1 plus 1 is the cube root of 2. And you're allowed to do that. The cube root of 2 exists. It's just a decimal, so it's going to be hard to graph that on our coordinate plane. So the next cube root that we know is, you can take the cube root of 8. So what do I have to have underneath my radical or what does my x value need to be so that x plus 1 is 8? It would need to be 7. So the cube root of 7 plus 1 is 8, which is 2. So that gives us some nice examples kind of on the positive side. We have one negative value, which is probably sufficient for us, but if we wanted to, we could do -2. The cube root of -2 plus 1. -2 plus 1 is -1. The cube root of -1 is -1. So I think that is fair enough. Let's just write that this was a decimal, so we can't graph it. But 4 points is enough to graph our function. I think kind of the rule that we normally follow is that 3 is enough. So 4 is just a little bit extra. So the first point is -2, -1. So let's go over -2, -1, and put a point. And then we have -1, 0, put a point there. We have 0, 1, put a point there. And then we had 7, 1, 2, 3, 4, 5, 6, 7, up 2. So it would probably be something right there. And now we can go ahead and fill in our line here. And we can kind of generalize what happened when we added 1 underneath of our radical sign. Our original function was that red line, and it looks like we moved to the left 1. And we can talk about the same thing. When we subtracted 5 underneath of our radical, here we started at the origin, and then we moved to the right 5. So that is just being able to identify our transformations, which we're going to write out more formally in our next example. But that's why I think it's a good idea to get a picture in our head or know our parent graph tables so that when it comes to graphing our transformations, our lives are a little bit easier here. So let's go down to example number 2. We want to graph a transformation of a radical function. Oh, I didn't do the domain and range of this one. So let's talk about that. Domain is my lowest x value to my highest x value. So x is going down over to the left to negative infinity, and it's going to the right to positive infinity. My domain is going to be all real numbers. And then again, range is if we're looking up and down at our graph. The lowest point my graph is going to go to is negative infinity. The highest point my graph is going to go to is positive infinity. So my range is all real numbers here as well. So we've identified the domain and range. Let's drop back down here and talk about our different types of transformations that we can have. So in this, we kind of have some empty space here. Make sure that you're writing out there are 3 different transformations that can be applied to any radical function. The one we saw in example 1, A and B, was this. We had a number underneath of our radical. So I always like to think of it as H. We have a horizontal translation. Now that horizontal translation is the one that goes backwards in our head. When we subtracted a number, it moved to the right. When we added a number, it moved to the left. So if you want to make a little note to yourself, that's the one that's backwards. You always can check yourself on Desmos as well. So if you're like, oh, I don't remember if that moves to the left or to the right, graph it on Desmos so that you can kind of like see the picture of what the graph is going to look like. All right. Now, we didn't see an example with a K value on the outside, but if H moves left and right, K is going to be our vertical our vertical translation. So K is going to move up and down, and that is the one that works normally how we think it would. If K is positive, it moves up. If K is negative, it's going to move down. And then the last thing that I just want to introduce so that we can be able to identify it, this A value on the outside of our function is either going to be a vertical stretch or compression. So my thing got a little bit blurry there. Oh, good. Okay. So if A is a positive whole number, if it's like greater than 1, it's going to stretch our function. And if A is a fraction in front of it, it's going to compress our function. So I always like to, on my graphs, include my parent function first, because then it makes graphing the transformations a little bit easier. So if I know my parent function of my square root starts at 0, 0, over 1, up 1, and over 4, up 2. So I just memorized those 3 points, and I can graph this here. That's just the square root of x. So what does our 3 different things applied to our function do? So this 1/2 here means that we have a vertical compression, is a vertical compression. I'm going to abbreviate that there. If we have this -1 underneath of our radical, it means that we move to the right 1. And then we have this -3 on the outside of our function, which means I need another color, -3. All right, so once we identify kind of our transformations of our problem, let's go ahead and graph our function. So our original parent function starts at the origin, but we now know our new function is going to move to the right 1 and down 3. So I always start with that first point. And if that is the only transformations, if you only have a horizontal and a vertical translation, or one or the other, or both, you can go ahead and just follow the same pattern of our parent function. Our second point was over 1, up 1. So you could go over 1, up 1. And then our third point was over 4, up 2. So you could go over 4, up 2. However, the thing that changes that pattern is our vertical compression here. So instead of following that over 1, up 1, over 4, up 2, we are now doing half of that. So the idea is that we're still going to go over 1, but instead of going up 1 this time, we're going to go up half of that. So half of 1 is 1/2. So I'm going to put a point here, and it's not really pretty, but it's going to be halfway between like our next square. And so then our next point was originally over 4, up 2. So I'm going to go over 1, 2, 3, 4. And instead of going up 2 this time, I'm going to go up half of 2. Half of 2 is 1, so I'm going to go up 1. And we can continue that pattern. It'll go on forever. Our next point is over 9 up 3, which would fit in here. So we could go over 9 up 1, 2, 3, but we have to do half of 3 this time. So we're going to go up 1.5. So that's the kind of the way that our vertical compressions or our vertical stretches change our function. They change that normal pattern from our parent function. And then our horizontal and our vertical translation just change the starting point of our graph. So instead of the origin, I move to the right 1 and down 3. Again, like always, you could always take a peek of what this graph is going to look like on Desmos, but now you kind of know how you can do it by hand if you are ever in the position where you need to. All right, we're going to do 2 more examples, which have to do with identifying our transformations of our functions. But example 3 is just going to raise the bar a little bit because we want to simplify our expression first. And our examples for part A and part B weren't very nice, so I went ahead and changed our examples to be a little bit nicer of what we're going to do for this class in identifying the transformations. So we talked about, let's write it up here, g of x could equal a times x minus h plus k. So we're looking for those points where we have a number out in front of our radical, maybe something underneath our radical, maybe something on the outside. But in this case, x is always by itself. So in our first example, we have this 4 out in front of x that I want to get rid of. And luckily for us, I can simplify this function by factoring out a 4. So I have the square root of 4 in parentheses x plus 4. I just factored out the 4. And now I can use my properties of radicals, things we've talked about before, to simplify this. Because my 2 terms are here are being multiplied, I can think of them individually. I can't take the square root of x plus 4, but I can take the square root of that 4. So square root of 4 is 2. I'm going to have to go over here and kind of go backwards. So I can pull out a 2 in front of my radical, and I would be left with x plus 4 underneath of it. And now we're looking a little bit more like our, I don't know what we call this. This is kind of like our formula or our equation of a radical function. So now that we've got it in the correct form, let's go ahead and identify our transformations. Here, our a value is 2. Because it is a whole number, it's not a fraction, it is going to be a stretch, a vertical stretch. And our k value here, not k, our h value here is positive 4. So h is a plus 4, which means it's going to go to the left 4. That one is a 1 that's backwards. So we would want to simplify anything we could underneath the radical first, and then we can identify the transformation. So let's go over to example B. This is just like example A, except for we have some more numbers here in our problem. But I'm still looking to try to get x all by itself. Right now it has a 9 out in front of it, but lucky for us, we can factor out a 9, and I'd be left with x plus 5. Underneath our radical, that 3 on the outside of the radical isn't going to be affected by that factoring out. So it's just going to come along for the ride. And now, lucky for us, we can take the square root of 9. We know that to be 3. So 3 is going to come out on the outside of our function. We have x plus 5 underneath our radical, and we're subtracting 3 at the end. So let's identify our transformations here. We have an a value, which is going to be a vertical stretch because it's a positive number. It's like a positive whole number. Our h value here is plus 5, so we're going to move to the left 5. And our k value is negative 3, so we're going to move down 3. So that is just being able to look at an equation and identify the transformation that's going to go along with it.